Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. I welcome everyone to the class of physics. Inshallah, today we will discuss about the chapter 13 of physics book, that is Modern Physics and Electronics. And before going to the topic of radioactivity, let's describe about the structure of a nucleus. So here we see there is a structure of nucleus that contains some amount of neutrons and some amount of protons. So I want to ask you a question that we know that same charges repel each other. So there are multiple number of protons. They should repulse each other by electrostatic force. So they should not exist in a one place. But why they are remaining so close inside a nucleus? What is holding them together? The answer is these protons are attached with neutrons in a compact place because of the strong nuclear force. That is, the repulsive electrostatic force between the protons are neutralized by the action of strong nuclear force, so that these protons can exist close together with neutrons inside the nucleus. So we're discussing that protons of nucleus repulse each other because of electrostatic force, and how this repulsive force is neutralized, because there is strong nuclear force present that acts between protons and neutrons. So now, so we say that to make the nucleus structure stable, we need both of them. We need both electrostatic force and the attractive strong nuclear force. So scientists found that an optimum ratio between the number of protons and neutrons is necessary to keep the nucleus stable, so that the attractive and repulsive force becomes equal, so the nucleus becomes stable. If the ratio is not maintained properly, if the number of neutron or number of protons outnumber the opposite one, then what will happen? There will not be the balance between these two kind of force. So as a result, the nucleus will become unstable. So the nucleus becomes unstable. And we know that among the starting from 1 to 118, there's 118 elements. All elements have at least one such isotope which is unstable. Every element has minimum single unstable isotope. That means its nucleus is unstable, and we say that all the unstable nucleus results in radioactivity. So how can we find from our daily experience such unstable isotopes or unstable nucleus? Let's start with the example of hydrogen. We know that there are three common isotopes of hydrogen. The first one is 1H1 protium, 1H2 deuterium, and 1H3 tritium. So 1H3 is the unstable one that has unstable nucleus, and that is also called radioactive isotope. And if we say in case of carbon, the carbon 12 and carbon 13, they are stable, while the carbon 14 is unstable, that is radioactive. So now we are actually digging into the concept of radioactivity. So what is called radioactivity? It is the process by which an unstable atomic nucleus loses energy by radiation process. So radioactivity is a process by which an unstable atomic nucleus converts into stable nucleus of another element, and it loses energy by this process, and this phenomenon of losing energy is called radiation. So in which isotopes or in which elements we find this phenomenon of radiation? We say that from the elements starting from mass number proton number 1 and ending up to 82, they both have stable and unstable isotopes. Sorry, I have a fault here. It should be atomic number, it should not be mass number. So elements having atomic number up to 82, they both have stable and unstable isotopes. That means we can find both stable version and unstable version of these elements, and it might contain several isotopes that is stable and several isotopes that is unstable. But we are saying that all of these elements have both stable and unstable isotopes up to 82 atomic number. So the lead that has atomic number of 82, it is called the heaviest stable element because it has a stable isotope. But when we start from bismuth, atomic number 83, and onwards up to 118, all the isotopes, all the elements have isotopes which are unstable. Starting from 83 and onwards, they don't contain any single stable isotope. All of the isotopes are unstable. That means they are considered as radioactive elements. That means starting from 1 to 82, they are called stable elements, and starting from 83 and onwards, they are called radioactive elements. So here we see that a periodic table. This periodic table shows that the stable elements are light blue in color. So starting from hydrogen and ending to lead, they all are stable isotopes, stable elements. But there are two exceptions between them: 43 technetium and 61 promethium. They don't contain any stable isotope, so they are always radioactive. So while we don't consider these two exceptions, we can say that starting from 83 and onwards, all of the elements are radioactive elements. Now, the phenomenon of radioactivity was discovered in 1896 by the scientist Henry Becquerel. So in your book there is a small misspelling. Henry, the spelling of Henry should be R-I, not R-Y. In your book that is referred as R-Y. That should not be. That should be R-I, Henry Becquerel. So the phenomenon was discovered by Henry Becquerel, and after that, Marie Curie and Pierre Curie, both husband and wife, they joined with Henry Becquerel to his research, and they contributed the research on radioactivity, and as a recognition, both three of them were awarded Nobel Prize in 1903 in physics. So now we say that radioactivity is a kind of change in nucleus, where the nucleus changes to a stable version of isotope of another element. So during this nucleus change, scientists have categorized this radioactive change or nucleus change into 6 or 7 kinds, but 3 are most common kinds. So the most 3 common kinds of radioactive decay are alpha decay, beta decay, and gamma decay. So by referring by the term decay, we are referring that that is actually a kind of change in the nucleus, and the nucleus is converting to another nucleus of another element. So this decay is actually referring to the nucleus change of nucleus. So the most 3 common kinds are alpha decay, beta decay, and gamma decay. We have discussed it, and in the alpha decay, the radiation type is called alpha radiation. In the beta decay, the radiation type is called beta radiation, and in the gamma decay, the radiation is called gamma radiation. So let's see a video.
Alpha, beta, and gamma radiations. Certain elements exhibit spontaneous emissions of radiations. Such substances are called radioactive substances. Here, one can observe the emission of the 3 major types of rays emanating from a radioactive substance placed inside a lead block.
So here we have taken a lead block, and inside it there is a radioactive substance present inside it, and in front of it there is a hole so that the radioactive rays can come out through this hole, and there is a special arrangement on both sides of it. There is a negatively charged plate and positively charged plate that is placed because it can deviate the positively charged and negatively charged radiation. So that can deviate and bend it. So the ray, if these two charges were not placed, if these two charge plates were not there, so the ray will travel straight and will fall on the zinc sulfide screen and produce a light, produce an emission of light from the screen. So a beam of light will be visible on the zinc sulfide screen. But when we provide two oppositely charged plates on both sides of it, we will find that instead of one, there is 3 spots visible on the zinc sulfide screen, because the negatively charged plate will attract the positively charged radiation, that is called alpha radiation, and the positively charged plate will attract and bend a type of emission or radiation that is called beta radiation, and another type of radiation that is called gamma radiation that will not bend towards any direction. That means that is not attracted by either positive or negative charge. So we say that there are 3 common kinds of radioactive radiations: alpha, beta, and gamma. And from this phenomenon we can also understand that the alpha radiation is positively charged, so that that is bended towards the negatively charged plate, and also we can assume that beta radiation is negatively charged, so that it is attracted towards the positively charged plate. So now inshallah we will discuss about the 3 kinds of radiation: alpha, beta, and gamma, and their properties. So what is alpha decay? Alpha decay is the radioactivity or the nucleus changing phenomenon in which alpha particles are released. So what is called the alpha particle or alpha ray? That is actually emission of helium nucleus through the space or vacuum. So what is called helium nucleus? We know that a helium that contains 2 protons, a helium atom that will contain 2 protons, and that will contain 2 neutrons, so that makes up the nucleus. So two protons and 2 neutrons make up the nucleus of a helium, and it should also contain 2 electrons to make up a helium atom, but we are not considering the 2 electrons, we are only considering the protons and neutrons together. So that is why that is called helium nucleus, because that it divides the electrons, so that is 2 plus, that is positively charged. So alpha particle is produced when uranium turns into thorium. So this when we see this alpha radiation, a common example is that when uranium turns into thorium by radioactivity change. So here we see that 92 uranium is converting to 90 thorium. So it is converting into a nucleus, an atom having less atomic number, and it by this process it is releasing 2 protons and 2 neutrons through the space. That is emitting a cluster of 2 protons and 2 neutrons that we can also consider as helium nucleus, that is positively charged. And what are the properties of this alpha decay? And during this alpha decay, these alpha particles ionizes the barrier intensively. That means on the barrier on which the alpha particles struck upon, and this barrier becomes intensively ionized because the alpha particles are positively charged, so that the barrier from it will take up electrons from the barrier surface, and the barrier surface will become charged, ionized. But alpha decay that doesn't have so much penetration capacity. It can be easily blocked by a sheet of paper, and through the air it can travel only 6 centimeters, and after that it cannot go further. So its penetration capacity is very much low. Then a new term comes here, that is phosphorescence. So how this term comes, because in the lesson of alpha decay we have learned, we came up with a new term, that is phosphorescence on zinc sulfide screen. So what is phosphorescence? Phosphorescence is a type of photoluminescence. That means that is a kind of process of emitting light where absorbed radiation, UV light, is re-emitted at lower intensity for up to several hours. That means some chemicals are capable of absorbing the light energy from UV light, and when the light source is turned off, these chemicals can emit a green light or lower intensity light for up to several hours. So some chemicals have such property. For example, zinc sulfide and strontium aluminate. We see that there are two powdery substances. Left one is zinc sulfide and right one is strontium aluminate. These two powdered particles have a capability to absorb visible light, to absorb energy from it, and when the light source is turned off in the darkness, they can emit light energy in a color of green, and some substances are capable to emit blue color or red color. That is also very common. So we see that the strontium aluminate has much more capacity to re-emit light than zinc sulfide. So where are these chemicals used? These chemicals are actually called phosphor chemicals because they can produce phosphorescence. That doesn't mean that that is made up of phosphorus, but these chemicals are capable of producing phosphorescence. That is why they are called phosphochemicals, and they're used in many toys, glow in the dark. You will see in many toys of the kids, for the kids, that emits light in the dark. So they are called glow in the dark toys. For example, that is a bird toy that can emit light in the darkness. And in CRT screens, CRT is a type of television screen, cathode ray tube, that is actually the older versions of televisions, and inside this TV it contains a glass tube, and in the inside inner surface of this glass tube, it contains phosphor powder. That is why when electron beams fall on the phosphor powder, that produces light, so we can see images on the screen. So these phosphor chemicals were used in CRT televisions, that older technology. And in the fluorescent bulbs, for example, tube lights or compact fluorescent bulbs or energy lights, the tube inside that contains a white powder, that is actually phosphor powder, that is used inside these lamps. And phosphor screens are also used in detection of ionizing radiation, as the example has been given previously. That is, a zinc sulfide screen is used for alpha decay detection. And now we will see a practical example that a fluorescent bulb contains phosphorescent chemicals. So there is a special kind of tube light made up that contains phosphor particles layered in half part of this lamp, and the half part of this lamp doesn't contain any phosphor chemicals. So half part contains phosphor chemicals and another half part doesn't contain any phosphor chemicals. So when we glow the light, what happens? Let's see. We see that half part of it, the part that contains zinc sulfide, phosphor chemical that glows white light, and the part in which there is no layer of phosphor powder that produces UV light. Actually what happens is that the tube light actually contains UV light, but due to the presence of phosphochemicals, these phosphochemicals absorb this the light energy from this UV light and then re-emit energy in form of white light. So we can see the white light coming from the tube light. So if there was no phosphochemical inside the tube lamp, we would not see any white light. We would only see the UV light from this. So now we will discuss a practical demonstration about phosphorescence in a video from Royal Society of Chemistry. Let's see.
I have over here a phosphorescent sheet. Now, at the moment it's being protected from the light with a cover. So, the light's off, please. Okay.
So that is actually the so-called zinc sulfide screen, and that is phosphorescence screen. He is opening it up.
I have a sheet here. Now, this is material that, when it's exposed to light, will glow in the dark. So if everyone with a laser pointer can please shine their light on this. Oh, very good. Some of them are nearly hitting it, yes. Very good. So, okay, and if we now have lasers off, what do we notice? Absolutely nothing. Okay, let's try some yellow light. So here I have a yellow laser. No one else in the audience, I don't think, has a yellow laser. And again, nothing happens. Let's try some green light. Still, absolutely nothing. Well, finally, I'm going to try a blue laser. Now, for a while, this was the only blue laser in the country until our professor of organic chemistry decided that he had to get one as well. Okay, and this one is actually able to excite the phosphorescent material. Now, you might not be able to see this unless you're...
So what is happening here is that if we give red laser light over the zinc sulfide screen, it doesn't show any luminescence after that. But when we provide UV light, or especially blue colored light on it, so that the zinc sulfide screen can absorb the imposed light on it and then can re-emit the light in form of green light.
Very close. I have another light source in my pocket. This gives out some UV light. This has even more energy. This allows me to write on it. In fact, I have another UV lamp here that's even larger. UV. So this light has enough energy to cause the sheet to glow.
So that means these phosphochemicals, they can absorb energy from a specific wavelength of light. They can absorb from the UV light or blue colored portion. They can absorb energy from the blue colored portion from the light, and they can re-emit the energy back at low intensity.
Okay. Very good. So the phosphorescent chemical in there was absorbing the light energy, but it needed to have good strong light to do this. Red light wasn't strong enough. It didn't have enough energy. Yellow light didn't have enough energy. Green light didn't have enough energy, but the blue did. Well, we've got one more sheet of this over here. Now, to use this one, I need a volunteer, please. Somebody close near the end. In fact, right on the end here. Good. Thank you very much. Very good. Now then, okay, we're going to take a picture of you. So, if you come over here for a moment, have the lights off, please. If you just stand here for the moment, we just need to take the screen off. Okay. Right. Just put this out of the way. Now, if you turn around, please, face the screen. Hands up, hands up. That's it, fingers out, on there, that's it, lovely. You stay there, legs apart. That's it. Legs apart. Very good. Right, now close your eyes. Ready, go. Very good, too. As you just stay still. And then move aside, please. Very good. Thank you very much.
So that is what phosphorescence screen means. That is made up of zinc sulfide or any other chemicals. They're called phosphochemicals. So now we will discuss about beta radiation or beta decay. So beta decay is a kind of nucleus change, radioactive change, where electrons are emitted. We say that beta particles are actually an electron. So when we say about beta radiation, that means there is a kind of nucleus change that involves the emission of electrons from the nucleus. So beta particles are produced when a neutron, when it happens? When a neutron disintegrates to produce a proton plus electrons plus antineutrino. We will not go into the technical details of it, but simply we say that beta radiation or beta decay happens when neutron converts into a proton so that it produces an electron and also produces antineutrino. So from this process we find the electrons coming out from the nucleus. And when a multiple number of nucleuses undergoes this change, so we can think that electron beams are coming out from the nucleus. And this beta radiation has ionization capacity at medium level. We said that ionization capacity of alpha decay is highest, alpha radiation is highest, and the ionization capacity of beta radiation is somewhat less than it. So it has medium ionization capacity, and beta radiation also have medium type of penetration capacity, so that it can be blocked by few millimeter thick aluminum sheet. So it has much more penetration capacity than compared to alpha decay or alpha radiation. So in your book you will study that beta decay can occur in two ways. So number one, that is called beta minus decay, and another one is called beta plus decay. So we will not go into the technical details of it, but what is called beta minus and what is called beta plus, we will know it. So beta minus decay is called the emission, or beta is kind of radiation when the nucleus emits electron and electron antineutrino, and when the neutron changes into a proton. That means beta decay is the process in which the neutron turns into proton, and along with this process it produces an electron and an electron antineutrino. And as an example of this process, we can say that when carbon-14 radioactive isotope of carbon that converts into nitrogen-14. So we say that carbon-14 is an unstable isotope or radioactive isotope, while the carbon-14 is the stable isotope of nitrogen. So carbon-14 is the unstable isotope of carbon, but nitrogen-14 is the stable isotope of nitrogen. So when it converts into this, this process is called beta minus decay. So here we see that. So the carbon-14 has turned into nitrogen-14. So a matter to notice is that carbon has proton number 6, but the nitrogen has proton number 7. So we see that an proton is added to it. So how this proton comes? This proton comes in expense of a neutron. So a neutron has gone, and instead of it a proton comes, so that the atomic mass number remains 14 equal. But along this process, what happens? An electron comes out as beta radiation, and also it produces an elementary particle called electron antineutrino. Okay, then we are discussing about beta plus decay. So what is beta plus decay? Beta plus decay is a radioactive change when it emits a positron and electron neutrino, and it happens when a proton turns into a neutron. That means simply there is a kind of nucleus change when proton turns into neutron, and during this process positron comes out and electron neutrino also comes out. And as an example of it, we can say that when magnesium 23 unstable isotope converts into sodium 23 stable isotope of sodium. So here we see that magnesium 23 unstable version of magnesium, we say that a stable magnesium should contain 24 atomic mass, but it contains 23 mass number, 23 atomic mass. So this 23 magnesium converts into 23 sodium, and here we see that magnesium has 12 protons and sodium has 11 protons. So during this change a proton has been lost. But in expense of this proton and neutron comes out, so that the atomic mass number remain conserved. And during this process, so we see that a proton turns into a neutron, and along with this process and a positron and electron neutrino comes out. So there are the two kinds of beta radiation. Actually this topic is very much higher level. It's from very much higher level. You will study it in university level, what is called beta minus or what is called beta plus, and why it happens, and what is called electron neutrino or antineutrino. That is actually advanced level concepts. And then gamma radiation. So we maybe we know that from our previous knowledge from class 8, what is called gamma ray or gamma radiation. So gamma ray is actually an electromagnetic wave. When it takes place, when a nucleus releases alpha or beta particles, it also radiates the excess energy in form of gamma radiation. So along with the other radiation processes, the excess energy is emitted in form of gamma radiation. So gamma radiation is chargeless. It cannot directly ionize atoms or molecules, but it has very much high penetration capacity. To block it, we need several centimeter thick lead sheet. Okay, so from our knowledge we can I hope that you can compare between the features of alpha, beta and gamma radiations. At first we talk about the symbol. So the alpha particle has a symbol of alpha, and there's beta and gamma from the Greek alphabets. These symbols are used. And what is about the mass? So gamma radiation, at first gamma radiation is chargeless and massless. It don't have any mass, it don't have any charge. But when we call about the mass of alpha radiation actually has the 4 times this amount. So why there is 4? Because we know that alpha particle contains 2 protons and 2 neutrons, and the mass of proton and neutron is approximately same. So we have taken here the mass of 2 protons. So we have taken a mass of 2 protons there. We have taken mass of a single proton and multiplied it with 4, because it contains 2 protons and 2 neutrons, collectively 4 particles are there. And in case of beta radiation, actually beta radiation is made up of numerous number of electrons. So the mass of electron here actually works as the mass of beta radiation. And when we talk about charge, so what is the charge of alpha radiation? A alpha particle contains 2 protons, and these 2 protons actually contributes to the amount of charge. So that is actually an alpha particle contains 2 protons, and the charge of 2 protons actually makes up the charge of alpha particle. And in case of beta, radiation. Beta radiation is made up of electrons, so the charge of single electron actually makes up the charge of beta radiation here. And penetrating power, we say that alpha radiation has very low penetration capacity, while the gamma has highest penetration capacity. But in terms of ionizing power, alpha radiation has highest ionizing power, and gamma radiation has lowest ionizing power. And shielding, that means by which material this rays can be blocked or suppressed. Alpha radiation can be suppressed or blocked using a paper or by skin surface. Beta radiation can be blocked by using 3 mm thick aluminum sheet, and gamma radiation can be shielded or blocked using 5 mm thick lead sheet. And what is the speed, traveling speed? Alpha particles has traveling speed comparatively slower than others, 10% of the speed of light in vacuum. And beta radiation is approximately very much fast and nearly closer to the speed of light. It ranges from 50% to 98% of the velocity of light. Here c means the velocity of light. And gamma radiation is actually kind of electromagnetic radiation, and it travels in speed of light. So now you have a homework that compare the features between alpha, beta and gamma radiations. So let's recall what we have learned from our today's lesson. At first, we have discussed about the concept of stable nucleus and unstable nucleus, what makes the nucleus stable, and when the nucleus becomes unstable and the unstable nucleus converts into stable nucleus of another element. This process is called radioactivity, and radioactivity is a phenomenon that is observed in all unstable isotopes. And then we call 82 elements as stable elements, starting from 1 to 82, without considering the two exceptions, promethium and technetium. And starting from 80 through 83, bismuth, to 118, all of them are radioactive elements. And radioactivity phenomenon was discovered by Henry Becquerel, and he was assisted by two other scientists, and won the Nobel Prize in 1903. And then we have discussed about the features of three most common kinds of radioactivity: alpha radiation, gamma radiation, and beta radiation. And that is the table that represents the comparison between these three rays. So that is your homework. Compare the features between alpha, beta, and gamma radiations. So thanks for attending the class. Allah Hafiz. Assalamu alaikum.